Hello everybody, this is your host, Odd Job Entertainment, known for not being able to make up my mind on whether or not I'm a Star Citizen channel or an engineering channel. And this video is no different, because while it is clearly a video about the incredible engineering of steel foundries, it is also a Star Citizen video in disguise. Feel free to discuss what you think that means in the comments below. Now imagine for a moment you are part of the first colony on a faraway planet. Being the tip of the spear of human space colonization, you're not able to receive any more resources from home. It's up to you and your crew to establish infrastructure and become self-sufficient as quickly as possible. Top on the list of priorities are water, food, shelter, and the material involved in making all of it, steel. You're tasked with getting that foundry operational. How do you do it? Many games today do teach the correct idea that steel is made from iron and carbon. This is true, but it's also very much a simplified representation. So to start, let's go through the process step by step. Iron is the fourth most abundant material in the Earth's crust. That's where we live, and it accounts for 1/3 of the total mass of our planet. Though, and this may surprise you, steel beams are not natural formations. Collecting iron is relatively easy compared to other kinds of mining. Because of the abundance of iron, surface mining is the most common. So digging a tunnel to find veins deep in the earth is much less common for iron than for other kinds of metals. Naturally occurring iron is found as hematite, magnetite, limonite, and siderite. The problem here is the iron we care about is bonded to all this extra stuff, or for our purposes, inert material. For it to be usable, we need to separate these impurities to reclaim the elemental iron. And the first step after collecting the iron is processing it into usable chunks. The ideal size for feeding a blast furnace is between 7 and 25 millimeters in diameter. This initial sorting is done by passing the raw ore over a sieve with holes increasing progressively in size. The pieces that fall within the ideal size range can go to the blast furnace from here. For small pieces, we can first try sintering. This is where the bulk ore is spread over a conveyor that passes under a heater filled by a coal coke breeze. This partially melts the ore and gets it to consolidate. Then, it can be broken up into usable pieces. The iron that is too small for sintering needs to be condensed by another means. And this is accomplished by moistening the iron-rich earth and then tumbling it in a rotating drum. This forms pellets that tend to be between 10 to 15 millimeters in diameter. These are perfect for feeding the blast furnace. Before they can get there though, they need to be dried and cured. This is done by baking the pellets in an oven at around 1200 degrees Celsius.
Oh, that's hot. That's hot.
For iron that is too big for the blast furnace, the material is sent through a crusher. This breaks up the larger chunks into more manageable pieces. The processes for both the large and small pieces aren't perfect, and everything passes through a similar sizing screen before being sent to the blast furnace. This means that we catch anything that isn't the right size, and those are processed again until everything fits our ideal range. Now, so far, nothing we've done has removed any of the impurities. We've done quite a bit of work to make sure everything is the right size, but why does that even matter? Well, surface area is one of the most important variables you can control that affects the heat transfer of a material. You can test this yourself. If you have an ice maker, get a timer and a thermometer and 2 cups of water with the same starting temperature. To 1 cup, add whole cubed ice. To the other, add the same mass of crushed ice. If you track the change in temperature for both glasses, you'll find that the crushed ice loses heat faster. You'll also notice that it melts faster. This is because the crushed ice has significantly more surface area than the cubed ice. This allows it to absorb heat much faster. The heat capacity of both forms of ice is identical, but the rate of heat absorption changes with the surface area.
I don't think you have any idea how fast I really am.
The same is true of our iron ore, just with different temperatures. If the pieces are too large, we have to invest a lot more time and energy to melt it. If everything is smaller, the iron will melt faster and more efficiently. There is a point of diminishing returns, however. Very fine particles become harder to move reliably, can be difficult to control for consistency, and are more likely to gum up machinery. As well, and most importantly, fine particles can block the very important flow of hot gas through the furnace. Large swings in particle size can make the melting less predictable. Also, iron isn't the only thing that gets sent into the blast furnace. Having everything be a homogeneous size means that the recipe is more easily maintained inside the blast furnace, where changes are going to be harder to make. Now, what is a blast furnace? I've used the term several times already, but how does it actually work? The genius of a blast furnace is that it combines a large oven and a conveyor belt in a way that neither has to ever stop moving. This is great because the energy investment to start a blast furnace is immense. It's much more efficient to start it once and keep it moving. Stopping it is disastrous, both for profits as well as the operators. There's an incredible level of stress placed on the materials that the blast furnace is made from, such that stopping it can permanently cripple it or otherwise cause serious damage. Any remaining ore hardens within, damaging the ceramic lining and requiring the blast furnace to be heavily remodeled to restart. Modern construction methods mitigate this to some degree, but there is still a huge risk being taken every time the furnace cools. Even when parts need to be swapped out, they are done in localized sections to prevent a full stop. This is why even starting a blast furnace represents both a commitment to present demand and to future supply to keep it running. Now, as for how it actually works, our pelletized iron is fed through the top by a rotating throat. In addition to our iron, we also feed limestone and coke. Coke is a very dense fuel made from coal and not a sugary drink that will kill you.
Diabetes.
The carbon it contains is critical in the formation of steel, but its use as a fuel makes this a perfect 2-for-1 for processing iron. Limestone is used here as flux. It helps remove impurities by bonding to them and forming slag, which can be screened out of the molten iron. Layer after layer of iron ore, limestone, and coke continually fill the blast furnace chamber. From top to bottom, the heat builds up to the melting point of the iron we're trying to collect. The top section stays solid, just like ice floating on your drink. But as the material progresses down, it gets hotter and hotter until it turns into a fiery soup of molten metals. The heat for this process starts with nozzles called tuyères that blow preheated air into the chamber. And this preheated air reacts violently with the coal coke and creates the intense combustion that fuels the furnace. Within this molten soup, a number of reactions are happening simultaneously. The oxygen atoms that came with the iron debond from the iron atoms and rebond to the carbon from the coal coke. This releases a lot of carbon dioxide and carbon monoxide. Slag forms by further contaminants bonding to the limestone. All of this results in a significant portion of the iron being liberated from these impurities. But there's a catch. The introduction of the carbon from the coal coke means that the iron that is liberated incorporates a significant portion of the new carbon. And when the tap is opened, the resulting iron mixture is approximately 4% carbon. This grade of iron can be cast into molds looking like loaves of bread or suckling piglets, hence pig iron. Ever wondered where that comes from? It comes from here. This is not the same as high-strength steel, which is an alloy of iron and carbon. The carbon content of this iron is too high, resulting in a brittle, almost glass-like metallic compound. It is, however, useful for many low-strength applications, and if poured into a different mold, can be made into cast iron cookware, engine blocks, and much more. Cast iron is also very dimensionally stable, naturally damping, and very rigid, so it can be processed into machine bases seen in nearly every modern manufacturing tool today. Cast irons were the first iron products to become widely available. Early technology struggled to produce high enough heat and maintain it for steel to be made for anything but very expensive and limited uses. The excess carbon that we've added has the side effect of lowering the melting temperature of the iron. And this made the combination of iron and carbon a natural consequence for early experiments, even without the ability to accurately study what was happening at the molecular scale. Early pioneers couldn't melt the iron directly, but if they added a little bit of organic material to it, it suddenly became possible. It's just that the resulting alloys are far from what modern steels require. Too much carbon and too brittle for widespread use. So if our goal is steel, then we need to do something about the excess carbon present in our iron alloy. Usable steels have anywhere from 0.04% up to 2.1% carbon. We're currently around 4% carbon, so at least half of it needs to go. The earliest mass manufacturing process that achieved this was the Bessemer converter. In essence, we have another large furnace with the ability to send air from the bottom into the molten iron ore. As the air moves through the molten metal, it bonds to the excess carbon and other remaining impurities to form various gases and slag. This exothermic reaction releases even more heat and keeps the iron molten even as the carbon content reduces. Now, if you're paying attention, we just did a bunch of work to pull oxygen off our iron atoms. Now we're reintroducing it. Well, oxygen in this environment is more prone to bond to carbon than to iron. So in the first furnace, we intentionally overdo the amount of carbon introduced to make sure that we get it all off of the iron. But now we need more oxygen to take care of the extra carbon. It's a lot like trying to get the perfect ratio of milk to cereal. And guess what? It gets even better.
But wait, there's more.
Because while it's theoretically possible to stop the process at just the right time to hit the desired amount of carbon in your steel alloy, in practice, that's very hard to do. So many of the early adopters of the Bessemer process struggled to produce usable steels. While the technology promised huge increases in production, it was failing to meet expectations. Then Robert Forster Mouchet improved on the process by oxidizing his steel until he was certain all the impurities and carbon had been removed. Basically, nothing left in the pot except for elemental iron. He essentially boiled the hell out of it. And at the end of the heating cycle, Mouchet would then introduce the exact amount of carbon and other alloying materials. This gave the needed ratios to make usable steel and was the missing link for the Bessemer process to revolutionize the industrial world. Today, steel foundries across the world still use a variation of the Bessemer process. The basic oxygen steel process takes the same kind of converter originally designed by Bessemer, and instead of using air as the oxidizing agent, uses pure oxygen. This has the benefit of not introducing nitrogen to the metal, which can embrittle the final product and was present when using hot air. Here the irony really comes full circle. We started with iron ore that had too much oxygen, so we heat it up and add carbon to pull it all off. But now we have way too much carbon, so we add oxygen until all the carbon is gone. But then we have no carbon left, so we add some more back in until we have the perfect Goldilocks ratio for our intended steel product.
Snip, snap, snip, snap, snip, snap.
Now, to be clear, these elements don't just sit next to each other in a soup. We start with oxygen atoms bonded to iron. We break those bonds by providing carbon and energy. The oxygen rebonds to the carbon atoms and is taken out of the equation entirely. We're left with elemental iron and too much carbon. The carbon sits in the interstitial spaces between iron-grain boundaries. We use more oxygen to carry away excess carbon, but it doesn't get the opportunity in this environment to bond to the iron. Left with too little carbon, we add just enough back in to tune the steel to the needs of the product. Consider the ingenuity of these early pioneers. Earlier processes were capable of making steel in small amounts. These inventors knew there had to be a better way, and if it were possible, they'd make the strongest known material commonplace. And they were right. Since then, we do have alloys that rival or supersede the steels made in this time. Aluminum has made commercial air travel possible with a better strength to weight ratio. Composites can push the envelope even farther, but nothing is as ubiquitous or world-changing as steel. I had an immense advantage over many others dealing with the problem inasmuch as I had no fixed ideas derived from long-established practice to control and bias my mind, and did not suffer from the general belief that whatever is right. Henry Bessemer. But let's come back to our scenario at the outset. We're on a faraway planet, and we need to make steel. It's going to be used in everything from spacesuits to habitations to vehicles. It's important to get it going quickly. First off, in the early days of mankind's iron production, we would brute force it by adding excess carbon and making cast irons. As discussed previously, the utility of these castings aren't as good as steel, but they're a stepping stone to better alloys. This, in essence, is what you're doing when you chuck your iron ore in the furnace with coal in Minecraft. The result is a cast iron that is brittle, but stronger than most metals your civilization will have seen by this point. And for our space explorers, cast iron is still a great start and the first proof of concept. As an early game process for our space colony, this allows you to make some structural elements, tools, and mechanisms, but they'd be limited in durability and strength. And this is further hindered by this process having little ability to truly remove impurities or to improve on the quality of our base ore. Things like nitrogen from the atmosphere or phosphorus from mining will contaminate the ore and weaken it. As well, the huge variety in ore sizes means that you'd be burning through coal like crazy just trying to get the ore to liquefy. So the next step in improving our production would be to add a crushing machine prior to the smelter. This doesn't double your ore like in modded Minecraft. Instead, it would improve efficiency and allow you to sort out bulk contaminants from the production line. These benefits result in more cast iron being made for the amount of coal we're using. The ability to size ores for smelting and a basic forge or furnace is what you would have seen in a blacksmith's workshop. This allows us to achieve small-scale production, but we're definitely not in the big leagues yet. To reach that kind of production, we really need coal coke and a blast furnace. Coke is made by baking coal in an oxygen-free environment. We can use our new cast iron to make a coke oven. We need a sealed chamber for the coal and a way to heat it. The chamber would still be made primarily from ceramics like fire bricks, but the cast iron is still a great material to help make the mechanisms that hold it all together and provide structure. We can use coal as it's found in the earth as fuel for the coke oven. We burn that outside the chamber so that it warms the chamber without mixing with it. We need to be sure to collect any off-gassing for future use, but other than that, it's just some time before we have our first batch of coal coke. In the meantime, we can upgrade our smelter into a blast furnace. This means providing a way to continuously feed it. We need to make tuyers for blowing the hot air, and we also need to collect some limestone from the environment to use as flux. We build our monstrous stack of brick and iron, and if we're smart, we'll try to reuse as much heat as we can. Residual heat from the coke oven can help preheat the air we feed into the blast furnace. We also need to make sure we include a way to recapture heat from the blast furnace itself. All of this takes a tremendous amount of energy, and we want to extract as much utility from it as possible. Feeding our blast furnace with coke instead of coal has a couple benefits. One, it's mostly pure carbon, so far fewer contaminants are introduced. Two, because it's much more pure, it's much more energy dense and enables us to reach higher temperatures and maintain them. Normal coal will contain some level of sulfur and produces a lot of smoke. Using coke is a cleaner fuel with no sulfur. The physical size of our blast furnace enables us to produce a lot more cast iron than we did before. We're not doing batch production anymore. Now we operate continuously.
Here comes the money.
Here we go.
Until we're advanced enough to go straight into steel production, we send the resultant cast iron into molds. These are most easily made with casting sand. We haven't yet unlocked the ability to make products that require more advanced alloys, but our throughput for the items available to us is dramatically higher. Since we know that the cast iron has too much carbon, we need to start preparing to strip that off. We know that we can get away with using air for this, but it is much more efficient to use pure oxygen. Oxygen can be made by electrolysis in small amounts. That's probably the process that most people are familiar with. That is simply running an electric current through water to separate it into its constituent parts. However, this is pretty inefficient, depends on us finding water, and so while it might do in a pinch, we want to start making oxygen in larger quantities. We could freeze the breathable atmosphere down to minus 185 degrees Celsius. At this extremely low temperature, oxygen will separate out from nitrogen and we can collect it as a liquid. This does require an atmosphere with oxygen, so it wouldn't be possible in every extraterrestrial setup, but if it's available, it's one of the best mass production methods we can do today. While we get oxygen production underway, we can also start construction on our BOSP furnace. This is a Bessemer process furnace, but we're planning to use pure oxygen instead of atmosphere. Once we have oxygen production in place and the BOSP furnaces built, we can start diverting our molten cast iron into steel production. Ideally, it feeds from one furnace to another, but if it did have to cool beforehand for whatever reason, be it a mismatch in rate of production or a delay in construction, we can use another furnace to preheat and melt the cast iron. The BOSP furnace is not the ideal tool for melting directly. We want to keep this one hot because the exothermic reaction between the carbon and the oxygen requires a certain level of input heat energy to take place. We can still further optimize efficiency by incorporating additional sizing processes like the sintering belt and the pelletizer to take better advantage of small particles and reclaim raw material that we were previously unable to process. This will lower fuel consumption of the following processes and pays dividends by lowering costs of production as the homogeneity of our input ore improves. When the carbon is burned off, we'll shut off the oxygen supply and add more carbon back in. The molten soup gets poured into molds before being allowed to cool into massive steel blanks. As it cools though, we need to pass it through several sizing dies that hammer and consolidate the material. Otherwise, our resulting metal becomes a porous mess. These can incorporate dies to directly make things like I-beams, sheets, cables, and square and round blanks of different sizes. The quality of our metal products is increasing with each addition to the infrastructure. Here, quality means a few things, because it represents both the purity and the specificity of our resultant alloy. They may all start as the same cast iron mix, but when they hit the BOSP furnace, we need to hone in on what we want to make. A spring steel is great for making springs, but it's not the best for every purpose. Different types of steel will also require different additives. Stainless steel, for instance, requires we add chromium. We can adjust the levels of silicon for elasticity, tungsten for hardness, cobalt for wear resistance, just as a few examples. As with many things, the final 20% of our steel production goes into the work of fine-tuning and optimizing. So if you want to make a high-quality item, a lot of that comes down to fine-tuning the properties of the material you're using. Are you making hard and rigid knives or rifle barrels? Or are you making structural components that need a little bit of flex and ductility? Are you making surfaces for food preparation or surgical implants? All of these require different mixes to achieve. My EDC knife uses an alloy called CPM154. It's 1.05% carbon, 14% chromium, and 4% molybdenum. Even beyond just the specific recipe, a major component in the steelmaking process comes down to heat treatment. That is something worth a video on its own. If you want to know more about how heat treatment affects steel, let me know in the comments below. In the context of starting a colony on some distant planet, the kind of infrastructure we've described can take years to put in place. We might be starting with one massive blast furnace and a BOSP follower. As we build up, we'll probably add more BOSP furnaces to handle continuous production of different grades of steel. An advanced colony can take this basic blueprint and scale it up to an entire industrial works district. But careful management of our product is going to be key to get there. If you're on the forward push of civilization, you can't just go to a local Walmart or Kelto for resupply. As our steel production ramps up in quantity, we'll want to start retrofitting and replacing some of the cast iron wherever steel is a more appropriate material.
Upgrades, people, upgrade!
In a real-world scenario, the first batches of steel are likely to be treated with extreme care. Success of the colony relies on the intelligent application of this invaluable material. Things like screws, structural beams, cookware, plumbing, doors, atmospheric seals, tools, and so much more all rely on steel. It's no exaggeration to say that steel is probably the most important resource after food, water, and air. It's also critical for the machinery that produces the food, water, and air. So really, chicken and egg, does it come before or after? It can be difficult to say. This video started as an effort to better understand for myself how iron goes from dirt to a finished product. I definitely have learned a lot along the way and have a much better appreciation for the incredible amount of infrastructure that goes into something so common like steel. If you learned something about how steel is made by watching this video, Drop a like and subscribe so you don't miss future content. I focus on the intersection of gaming, technology, and engineering. I also want to give a shout out to our channel members. Orbital Bombardiers and Up get a mention in each and every piece of content I release. So thank you. Your contribution directly helps make content like this possible. Until next time, this is Odd Job Entertainment, signing off.